Is it possible to overload power transformers? Introduction. Power transformers are indispensable components within electrical power systems, serving as crucial links in the transmission and distribution of electricity. These static devices play a vital role in adjusting voltage levels to ensure efficient long-distance power transfer and safe delivery to end users. While designed for reliable operation under specific load conditions, it is important to understand their limitations, particularly concerning the phenomenon of overloading. This report delves into the question of whether power transformers can be subjected to loads exceeding their rated capacity, exploring the causes, consequences, and preventive measures associated with such occurrences. Understanding these aspects is paramount for maintaining the integrity of electrical systems and ensuring a consistent power supply. Understanding the basics. What is a power transformer? A power transformer is essentially a static electrical device that facilitates the transfer of electrical energy between two or more circuits through the principle of electromagnetic induction. Unlike many other electrical machines, it lacks moving parts, relying solely on the interaction between magnetic fields and electrical conductors. At its core, a power transformer comprises two or more coils of wire, known as the primary and secondary windings, wound around a shared magnetic core. This core is typically constructed from stacked layers of thin silicon steel laminations, a design that minimizes energy losses due to eddy currents induced by the alternating magnetic field. The primary function of a power transformer is to efficiently alter the voltage levels of alternating current, AC, electricity. This voltage transformation is achieved through the ratio of the number of turns in the primary and secondary windings. Step-up transformers increase the voltage, which is crucial for long-distance transmission as it reduces current and consequently minimizes energy loss due to resistive heating in the power lines. Conversely, step-down transformers decrease the voltage to safer and more usable levels for distribution to industrial, commercial, and residential consumers. Beyond voltage adjustment, transformers also provide galvanic isolation between circuits, enhancing safety by preventing direct electrical connection. Power transformers are employed across a wide spectrum of voltage applications, ranging from high-voltage transmission lines operating at hundreds of kilovolts, e.g., 110 kV to 750 kV, to lower voltage distribution networks supplying power at levels suitable for various end uses. The consistent emphasis on voltage transformation across various sources underscores its fundamental importance in the electrical grid. Any deviation from the intended voltage and current due to overloading would directly impact the efficiency and safety of the entire system. The use of laminated cores to mitigate eddy currents is also a critical design aspect. When a transformer is overloaded, the increased current intensifies the magnetic field, potentially leading to higher induced eddy currents within the core. This, in turn, results in increased resistive heating in the core material itself, further exacerbating the thermal stress on the transformer. Defining the danger. What is transformer overloading? Transformer overloading occurs when a power transformer is subjected to an electrical load that surpasses its designed and rated capacity, provided passage. This situation inevitably leads to an increase in the flow of electrical current through the transformer's windings, provided passage. The immediate consequence of this elevated current is a rise in the internal temperature of the transformer, provided passage. This temperature increase is primarily due to the resistive heating within the windings and the core, which is directly proportional to the square of the current flowing through them. The provided passage clearly establishes a direct link between overloading, increased current, and a subsequent rise in temperature. This relationship is a fundamental principle governed by Joule's law, which states that the heat generated in a conductor is proportional to the square of the current and its resistance. Therefore, a transformer's rated capacity signifies the maximum current it can safely handle without exceeding its thermal limits. Any load demanding current beyond this rating will inevitably lead to overheating. The reasons why: common causes of transformer overloading. Several factors can contribute to the overloading of power transformers. One common cause is an unexpected surge in demand on the electrical system, provided passage. This can arise from various scenarios, such as increased electricity consumption by existing users during peak hours, the connection of new, large loads to the grid, or industrial processes requiring more power than initially anticipated. Another significant cause of overloading can be faults within the electrical system. Short circuits or ground faults occurring downstream from the transformer can create a path of very low resistance, leading to a sudden and substantial increase in current flow through the transformer. This rapid increase can quickly exceed the transformer's rated capacity, resulting in an overload condition. Furthermore, situations can occur where a transformer was initially not appropriately sized for the connected load, and as the demand on the system grows over time, the transformer becomes increasingly susceptible to overloading. These causes highlight the critical importance of both accurate load forecasting and robust system protection mechanisms. Overloading is not always a gradual process. Sudden faults can lead to immediate and severe overloads. While predictable increases in electricity demand can be addressed through infrastructure upgrades and the deployment of appropriately sized transformers, unforeseen events like electrical faults necessitate the presence of effective protection systems to prevent catastrophic transformer failures resulting from overload conditions. Feeling the heat. Consequences of transformer overheating. When a power transformer is overloaded, the increased current flow generates a significant amount of heat within its windings and core. This heat generation can surpass the capacity of the transformer's cooling system to dissipate it effectively, provided passage, may surpass the transformer's cooling capacity. Transformers employ various cooling methods, including natural air cooling, forced air cooling using fans, or oil immersion with radiators or forced circulation, to manage their operating temperature. However, during an overload, the rate of heat generation exceeds the rate of heat dissipation, leading to a rise in the transformer's temperature. This overheating can have several detrimental impacts on the transformer's operation. Firstly, the electrical resistance of the windings increases with temperature, leading to further energy losses and even more heat generation. Secondly, and more critically, excessive heat accelerates the degradation of the transformer's insulating materials. Furthermore, other components like bushings, which provide insulated terminals for connections, and tap changers, used for voltage adjustment, can also be damaged by prolonged exposure to elevated temperatures. The efficiency of the cooling system is directly challenged by overloading. While a well-designed cooling system can manage a certain degree of overload for a limited period, sustained or severe overloading will inevitably overwhelm its capacity to remove heat effectively. The heat generated is proportional to the square of the current, meaning that even a relatively small percentage increase in current can result in a significantly larger increase in heat, placing a substantial burden on the cooling system to maintain safe operating temperatures. A threat to insulation, degradation and potential failure. Prolonged or severe overheating resulting from transformer overloading poses a significant threat to the integrity of the transformer's insulation materials, provided passage. High temperatures can compromise the insulation materials. These materials, typically consisting of paper, varnish, and insulating oil, are crucial for preventing short circuits between the windings and between the windings and the core. When subjected to high temperatures, the insulation undergoes a process of degradation, becoming brittle and losing its dielectric strength, which is its ability to withstand electrical stress. As the insulation weakens, it becomes more susceptible to electrical breakdown. Eventually, this degradation can lead to short circuits occurring within the transformer, which can cause significant damage to the windings, core, and other internal components. Ultimately, insulation failure is a primary cause of permanent transformer damage and can lead to the complete failure of the transformer, provided passage. Potential transformer failures. The insulation is truly the lifeline of a transformer. Its degradation is a cumulative process that is significantly accelerated by elevated temperatures. Even seemingly minor, repeated overload events can contribute to a gradual weakening of the insulation, ultimately reducing the transformer's operational lifespan. The chemical properties of the insulation materials change at higher temperatures, leading to a reduction in their ability to withstand electrical stress. This weakening makes them more prone to break down under normal operating voltages, eventually culminating in catastrophic failure of the transformer. Time takes its toll, reduced operational lifespan. Repeated or extended overloading has a direct and detrimental impact on the operational lifespan of a power transformer. The accelerated degradation of insulation and other critical components due to the elevated temperatures associated with overloading leads to premature wear and tear. As the insulation deteriorates more rapidly, the likelihood of failure increases, effectively shortening the time the transformer can operate reliably. This reduction in lifespan carries significant consequences, including increased maintenance costs due to the need for more frequent repairs or replacements, provided passage, leading to increased maintenance costs. Furthermore, transformer failures often result in operational downtime, which can be extremely costly for industries, utilities, and other entities that rely on a continuous and stable power supply, provided passage, and operational downtime. The economic implications of overloading are considerable. While a short-term overload might appear to be a minor issue, the long-term costs associated with a reduced lifespan, increased maintenance requirements, and the potential for costly operational outages far outweigh any perceived benefits. Transformers are substantial capital investments with expected lifespans spanning several decades under normal operating conditions. Overloading acts as a significant stressor that accelerates the aging process of the transformer, leading to a lower return on investment and increased operational risks over time. Built to handle. The role of transformer design and cooling. The design, construction, and the efficiency of the cooling system of a power transformer play a critical role in its ability to withstand temporary overload conditions. A well-designed transformer, incorporating high-quality insulation materials and a robust core structure, is better equipped to manage the stresses associated with excess loads, provided passage. A well-designed transformer can better manage excess loads. Similarly, an efficient cooling system, whether it relies on natural convection, forced air, or oil circulation with radiators, can effectively dissipate the additional heat generated during a short-term overload, preventing the temperature from reaching damaging levels. Different types of cooling methods offer varying capacities for heat removal. For instance, an oil-immersed natural air-cooled (ONAN) transformer typically has a lower overload capacity compared to an oil-immersed forced air-cooled (ONAF) or an oil-immersed forced water-cooled (OFWF) transformer. The design and cooling capabilities are therefore crucial factors in determining a transformer's tolerance to temporary overloads. This highlights that not all transformers possess the same capacity to handle overloads. Their specific design and cooling mechanisms must be carefully considered when evaluating their operational limits. The thermal management capabilities incorporated into the transformer's design serve as the primary defense against the damaging effects of overloading. A more sophisticated cooling system enables a higher permissible overload for a limited duration without exceeding critical temperature thresholds. The nature of electricity, impact of different load types. The characteristics of the electrical load connected to a power transformer can significantly influence the likelihood and severity of overloading. For example, inductive loads, such as electric motors, often draw significantly higher inrush currents during startup compared to their normal operating current, provided passage. For instance, surge currents can exacerbate the situation. These transient surge currents can cause temporary overloads on the transformer, even if the steady-state load is within the transformer's rating. Similarly, nonlinear loads, which are increasingly common with the proliferation of electronic devices, can generate harmonic currents that circulate within the electrical system. These harmonic currents can lead to increased losses and potential overheating in the transformer, even if the fundamental frequency load appears to be within the limits. Furthermore, the power factor of the load, which is related to the phase difference between voltage and current, can also impact the current drawn by the transformer for a given amount of power delivered. A low power factor necessitates a higher current to supply the same power, potentially increasing the risk of overloading. The type of load connected to the transformer plays a crucial role in its operating conditions and its susceptibility to overloading. Therefore, a thorough understanding of the load characteristics is essential for selecting an appropriately sized transformer and implementing effective measures to prevent overloading. A transformer supplying predominantly inductive loads might experience frequent transient overloads during motor starts, thus requiring a higher short-term overload capacity. Likewise, harmonic currents generated by nonlinear loads can elevate the effective current and losses within the transformer, even if the apparent power remains within its rated limits. External factors: the influence of ambient temperature. The ambient temperature of the environment in which a power transformer operates can significantly affect its ability to dissipate heat and, consequently, its susceptibility to overloading, provided passage. Higher ambient temperatures can hinder the transformer's ability to dissipate heat effectively. When the surrounding air temperature is high, the temperature difference between the transformer's hot internal components and the ambient air is reduced. This smaller temperature gradient hinders the efficiency of the cooling system, making it more difficult for the transformer to shed the heat generated by its operation, provided passage, making it more vulnerable to overload conditions. In hotter climates or in enclosed, poorly ventilated spaces, the transformer's cooling capacity is diminished, increasing the risk of overheating even under normal load conditions. This effect becomes even more pronounced when the transformer is subjected to an overload. To account for the impact of high ambient temperatures, manufacturers often provide temperature derating guidelines for their transformers. These guidelines specify the maximum permissible load at different ambient temperatures to ensure that the transformer's temperature limits are not exceeded. Environmental conditions are a crucial factor in transformer operation. A transformer operating in a high ambient temperature environment has a reduced capacity to handle overloads compared to an identical transformer operating in a cooler environment. The temperature difference between the transformer's hottest parts and the surrounding air drives the heat transfer process. A higher ambient temperature reduces this temperature difference, impeding the cooling process and making the transformer more prone to overheating under the same load conditions. Prevention is key. Best practices to avoid overloading. Preventing transformer overloading is crucial for ensuring the long-term reliability and lifespan of these vital components. One of the most effective preventive measures is to ensure that the transformer is appropriately sized for the expected maximum load. Provided passage, it is essential to ensure that the transformer is appropriately sized for the expected load. This involves accurately estimating the current and future power demands of the connected equipment and selecting a transformer with a rated capacity that comfortably exceeds these demands. It is also prudent to consider potential future load growth when determining the appropriate transformer size. Proactive measures such as proper sizing represent the most effective strategy for preventing overloading in the first place. Selecting a transformer with a capacity that comfortably exceeds the anticipated maximum load provides a crucial safety margin, reducing the likelihood of overloading under normal operating conditions and even during moderate surges in demand. Keeping a close watch. The significance of load monitoring. Regular monitoring of a power transformer's load and operating temperature is essential for detecting potential overloading situations before they escalate and cause damage. This monitoring can involve measuring the current flowing through the transformer, the power being delivered, and the temperature of critical components such as the windings and the oil. Modern electrical systems often incorporate sophisticated monitoring devices and systems that can provide real-time data on these parameters and trigger alarms if overload conditions are detected. Continuous monitoring provides valuable insights into the transformer's operational status, allowing for timely intervention to prevent overloading and potential failures. Real-time data on load and temperature enables operators to identify trends and anomalies that might indicate an impending overload. This allows them to take corrective actions, such as reducing the load or investigating the cause of the increased demand, before the transformer reaches critical operating limits. Regular care. The importance of maintenance and testing. Conducting regular maintenance and testing on power transformers is vital for identifying potential problems early that could either cause or exacerbate overloading. Provided passage. Conducting regular maintenance and testing can identify potential problems early. Routine checks can reveal issues such as degraded insulation, loose connections, or malfunctions in the cooling system, all of which can contribute to increased operating temperatures and a higher susceptibility to overloading. Timely interventions based on the findings of these maintenance activities can prevent failures that might otherwise occur due to overloading. Provided passage, allowing for timely interventions that prevent failures. Common maintenance practices include testing the insulating oil for properties like dielectric strength and moisture content, measuring the insulation resistance of the windings, and conducting thermographic surveys to identify hotspots. Preventative maintenance is crucial for ensuring the long-term health and reliability of transformers and for mitigating the risk of overloading. Addressing minor issues proactively can prevent them from escalating into major problems that could lead to overloads or failures. Regular checks can identify early signs of deterioration in the transformer's components, such as insulation weakness or cooling system inefficiency. Addressing these issues promptly ensures that the transformer operates within its design parameters and is better equipped to handle normal loads without the risk of overheating due to underlying problems. In case of emergency, implementing overload procedures. Establishing clear emergency procedures to be implemented when a power transformer is detected to be in an overload situation is crucial for mitigating the associated risks. Provided passage, establishing procedures to handle overload situations. These procedures may include actions such as immediately reducing the load on the transformer by disconnecting non-essential circuits. Provided passage, such as reducing the load. In cases of severe overload, it might be necessary to temporarily shut down the transformer to allow it to cool down and prevent permanent damage. Provided passage, or temporarily shutting down the transformer. Well-defined emergency protocols ensure a swift and appropriate response when an overload is detected, minimizing the duration and severity of the overload and protecting the transformer from potential damage. When an overload is detected, immediate action is necessary to prevent the temperature from exceeding critical limits. Predefined procedures ensure a swift and appropriate response, minimizing the duration and severity of the overload and protecting the transformer from damage. Short bursts. Understanding permissible overloads. While prolonged overloading is detrimental, power transformers can sometimes be designed to handle short-term overloads for limited durations. The specific overload capacity and the permissible duration vary depending on the transformer's design, its cooling system, and the ambient temperature. Provided passage. The specific overload capacity varies based on the transformer's design and cooling system. Some transformers, for instance, might be able to tolerate an overload of up to 1.2 times their rated capacity for a brief period, such as a few minutes or hours. However, it is crucial to recognize that this is not a universal standard and should never be assumed. Provided passage. However, this is not a universal standard. The permissible overload limits for a specific transformer must always be verified by consulting the transformer's nameplate or the manufacturer's technical documentation. Exceeding the rated capacity, even for a short period, puts stress on the transformer and can contribute to long-term degradation. Therefore, relying on this capacity as a regular operating mode is not advisable. Conclusion. In conclusion, it is definitively possible to overload power transformers. Subjecting these critical components to loads exceeding their rated capacity leads to increased current flow and a subsequent rise in internal temperature. This overheating can have severe consequences, including the degradation of insulation materials, a reduced operational lifespan, increased maintenance costs, and potential transformer failure. While some transformers may be designed to handle short-term overloads, this capacity is limited and specific to each unit. Therefore, it is paramount to implement best practices to prevent overloading, including proper transformer sizing, regular load and temperature monitoring, consistent maintenance and testing, and the establishment of emergency overload procedures. By understanding the causes, consequences, and preventive measures associated with transformer overloading, Operators can ensure the longevity, reliability,